Okay, so this video is going to be a continuation of a problem that we had started, and we had solved that problem using one particular approach, and here we are going to take a slightly different approach in solving the problem, and hopefully by doing that we will be able to clarify some of the concepts that we want to deliver through these different problems. So the problem goes as follows. There are two masses, particle masses m1 and m2. They are connected by a inextensible massless string, and impulse acts on the mass m2 in a direction perpendicular to the string, and the magnitude of the impulse is m2 times v naught. So so the question is, what is the resulting motion of the system, and number two is, what is the tension in the string. So this problem was solved in the prior video using the overall motion of the system of particles. We used the linear impulse momentum equation for the overall system of particles, and we also used the angular impulse momentum equation for the system of particles about the center of mass, and we obtained the results. So I would encourage you to go to that video and take a look to get an overview and background of how we had solved it prior. Now in this video our approach is going to be a bit different, in the sense that we are going to do a more particle by particle analysis. We will see how this impulse affects the velocities of the individual particles, and from there we are going to piece together the overall motion. Like any valid approaches, if the approaches are valid, they should lead to the same answer, and so we will verify that indeed with this approach, which is a little bit different, we'll arrive at the same solution as before, basically showing or confirming that in both approaches the underlying physics is being consistently captured and leading to the same solution. So let's proceed with this. So the first part of the problem will actually, I'm not going to repeat the determination of the center of mass, although we are not going to be very reliant on the center of mass in this approach, but still we will bring in the location of the center of mass at a certain point in the problem, and because we are going to do that, then we want to just, instead of repeating the calculation, we want to show how the center of mass or what the location of the center of mass is. So for this particular problem with m1 m2, the length of the string being L, and the way it is right now, initially, that is, the location of the center of mass is given by this distance d from m2, and c is the center of mass, and this distance was found out to be m1 times L divided by m1 plus m2. So that calculation is going to be at some point used, but not right away. The way we are going to proceed right now is that we are going to look at we are going to look at this problem, as I mentioned, from a particle by particle basis. What that means is we are going to see how this impulse, which is f hat equals m2 v naught, how this or what effect it has on mass m2 and m1 individually. So in order to do that, we note that when the impulse acts on this m2, and I have shown that the direction of the impulse is perpendicular to the string, because it is an inextensible string, and a string cannot transmit forces in the compression direction. So strings cannot be compressed. They can supply forces when in tension, but also that this impulse is perpendicular to this string at this instant. This means that no part of this impulse can be transmitted to this mass m1. So what it means is that the entire impulse f hat equals m2 v naught will go into changing the momentum of m2. So what that means is that we can find out the net velocity of m2 at the instant right after the impulse takes place. So the velocity of m2 right after impulse. So if I consider this as my x direction and this as my y direction and the unit vector along the x direction to be I and the unit vector along the y direction to be j, as is standard, then I can say that m2 v naught I, that's the impulse, is equal to the change in momentum of m2, which is m2 v2I minus 0, because the particles are at rest initially. So this tells us that v2 is equal to v naught. Okay, so the net velocity that the particle m2 gets as a result of this impulse is v naught. Now, because the string does not transmit any impulse to m1, then we can say that right after, and when we say right after, we mean at the instant the impulse is applied. Right after impulse, v1 is equal to 0. So v1 still does not have any velocity, and v2 has a velocity of v naught. Now with this, then we can find out the velocity of the center of mass. So we can say that therefore m1 plus m2 vcm is equal to m1 v1 plus m2 v2, which is equal to, this goes to 0 because v1 is 0 and v2 is v naught, so m2 v naught, which means that vcm is equal to m2 v naught divided by m1 plus m2. Okay, again we are not taking the the center of mass approach here. Let me just show the center of mass, and we have assumed that the center of mass is at a distance d and this distance was determined. D is equal to m1l divided by m1 plus m2, but nevertheless we can find out the center of mass velocity. Okay, and this will be useful. Now now this velocity v naught that the mass m2 has attained, we need to interpret this carefully. This is the net velocity that m2 has attained, and v1 equals 0 should also be considered as a net velocity that m1 has attained. The reason we say net is because when an impulse acts on the system, and because the impulse is offset from the center of mass, it not only produces a linear impulse, but it also produces a rotational angular impulse. And so when we say that the velocity of v2 is v0 at the instant after the impulse, this is a combination of the velocities that are produced by the linear impulse and the velocity that is produced by the angular impulse. So v2 equals v0 and v1 equals 0 is the effect of the velocities produced is the net effect, I would say, net effect of velocities produced by the linear impulse f hat and the angular impulse about c, which is f hat times d. Okay, so we need to interpret these velocities carefully. Now the linear impulse produces a uniform velocity for both the masses because it's a velocity that is attributed to the center of mass. It should be considered as a velocity, as a common velocity for all the particles. Okay, that's the linear velocity that is produced. The angular impulse produces an angular velocity which causes the difference in the velocities of m2 and m1. So if we consider the difference in the velocities between m2 and m1, that difference is not because of the linear impulse, but it is rather because of the angular impulse. The difference in velocities are caused by the angular impulse. So when it comes to finding the angular velocity, we note the following. That is, the velocity here is v0, okay, but this is essentially equal to vcm plus omega times d, where this is the center and the center is at a distance d from m2, and so it is at a distance of l minus d from m1. And here the velocity is 0, which is a combination of the center of mass velocity vcm, which is the same as this one, but then an angular velocity, or rather another velocity which comes from the angular velocity omega l minus d. So in fact v0 is vcm plus omega d, and this zero velocity is vcm minus omega l minus d. And so you can see that the difference in the velocities from v0 to 0 is nothing but, so the velocity difference between m2 and m1 is equal to v0 minus 0 is equal to v0, which is also equal to vcm plus omega d minus vcm plus omega l minus d, because the velocity in m1 is vcm minus omega l minus d. So these two cancel, and what you have is omega times l. Okay, so the difference in velocities is omega times l. So the angular velocity omega times L. L is this distance. So then we get omega to be equal to V naught over L. We also note the following. We also note that if you consider the velocity V naught, okay, and if you draw a line connecting the tip of the velocity V naught to the zero velocity at m1, right, if you join this line, so this is V naught and here it is 0, then you can use similar triangles to find out what this velocity is. Okay, so the tip of the velocity is going to be on the line joining V naught to 0. Okay, so there is a uniform velocity gradient which is produced as a result of this impulse, and velocity gradient, there is a velocity gradient because we not only have a linear impulse but we also have an angular impulse. If it was only a linear impulse, the velocity would be the same throughout, okay, from m1 to m2. So that's the angular velocity. So we have the VCM, we have the angular velocity, and then we are interested in finding the tension, and we can proceed with the tension, and the tension force is like this. It is acting like this and it is acting inwards like that. Now the tension force can be then formulated, because the whole thing is turning about the point C. That is how we have formulated it, that the center of mass is translating and the whole thing is rotating about the center of mass. Then the tension force is equal to m omega squared d, so m2 omega squared, and the distance of m2 from the center is d, so that is m2 into omega squared is V naught squared over L squared, and d was found out to be m1 L divided by m1 plus m2, so this gives us m1 m2 V naught square divided by L times m1 plus m2. And we can show that if we can also formulate the tension as m1 times omega squared times L minus d, we can do that, and that's going to give us m1 times V naught squared over L squared times, if d is this, then L minus d is going to be m2L divided by m1 plus m2, so that is going to give us the same expression, m1 m2 V naught squared divided by L m1 plus m2, which is expected. The tension is expected to be the same. There is no mass in this string, so the same tension applies on both the particles. Now there is another way to look at this problem of finding the tension. It can be a little bit confusing when you get to calculating the tension, because one can think that, well, this tension should be calculated as mass 2 times V naught squared or omega squared times L, because this point is the point the particle m1 does not have a velocity at that instant. But that is not correct, because we have to keep in mind that this motion is composed of a linear motion and a rotation motion, and the linear motion does not lead to any tension. If the two particles m1 m2 move with the same velocity vcm, right, it does not produce any tension in the string. So the tension in the string is only created by virtue of the angular impulse, which creates an angular velocity. So that's why we need to consider the rotation about the point C. But to elucidate this further, another approach that we can take another approach to find the tension. Now let us say that we make the assumption that we don't know about which point we should consider the rotation to take place. So let's say this is M1, M2. This is let me just check something here. Yeah, the center of mass is C, and there is a rotation of this rigid body. Now let's say that we are not sure if we should consider the CM as the center of rotation, or if there is some other center of rotation that we should be considering. So we can take some arbitrary point, let's say C prime, and say that C prime is at a distance of D2 from M2 and a distance of D1 from M1. Okay, we understand that the actual center of mass is at a distance of D from M2. The reason we are pursuing this is to understand the tension calculation a little bit better. Now let's say we don't know about which point we should consider the rotation of this rigid body, of this, not this rigid body, but this system of particles. We know, however, that the tension are at this instant, or at actually all instants, they are equal and opposite. And we say that let's say there is it is at a distance of D2 from M2 and D1 from M1. Then we can say that D1 plus D2 is equal to L. We can also say that because the two tensions are the same, T is equal to M1 omega squared D1, and it is also equal to M2 omega squared D2. Right? So from this we get M1 D1 is equal to M2 D2, and therefore we get D1 plus, and D2 would be M1 D1 divided by M2 is equal to L. This is substituting into the first equation, which then gives us D1 to be M2 L divided by M1 plus M2, and it would give us D2 to be M1 L divided by M1 plus M2. Okay, and we see that indeed this quantity is same as D, the location of CM from M2. So indeed we are saying that we should consider the the center about which the system is rotating to be the center of mass of the system, and so then we can therefore say that the tension is equal to M1 omega square. So this is D2, so therefore we can say D2 is equal to D, and D1 is equal to L minus D, right? And so we can say that the tension is equal to M1 omega squared L minus D is equal to M2 omega squared D. Okay, and we have just shown these calculations and they give us the same tension in the string. So you see, if you consider this approach to the problem, you see that we are not really dealing with the center of mass, and we are not really applying angular impulse momentum equation. We are just applying the linear impulse momentum equation, and that too we are applying on a particle by particle basis. As we did over here, we applied the linear impulse momentum equation on particle m2. That gave us the velocity of the net velocity of m2 after the impulse. We also applied it to m1 to give us the net velocity of m1 after the impulse, and then from there we kind of reconstructed what would be the angular velocity, because we said that the velocity difference is equal to V0. The net velocity difference is equal to V0, and that is related to omega times L, from which we were able to find the angular velocity. Okay, and then we went ahead and found out the tension in the two strings. Here we first assumed that the center of mass is good enough to consider the whole system to be rotating about, which is a natural choice. However, here what we did is we then said that let us relax that assumption and say that there is some point C prime about which the rotation is taking place, and assuming that the d1 plus d2 equals, not assuming but imposing d1 plus d2 equals L, and imposing the fact that the tension is the same on the two particles, we found that indeed that center of rotation coincides with the center of mass, and hence it also confirms the tension calculation that we did earlier. So that's the end of this video. So essentially, for this two particles connected by string problem under the influence of a linear impulse on one particle, we have addressed this problem using two methods. The first one used the or applied the linear impulse momentum and angular impulse momentum equation on the overall system, and then derived the parameters of motion, or the nature of the motion, resulting motion, and the tension forces. And then what we did is we applied the linear impulse momentum on particle by particle basis. We did not rely in this second approach on the angular impulse momentum equation, but we came up with the same answer as before. And you can verify that the answers that we have here with respect to the angular velocities, the center of mass velocity, the tension expressions are the same as that in the previous method. So that brings us to the end of this video. Thank you.